Good afternoon. My name is Paul Linnemolder. I am the Senior Director of Research and Development at Holland Company. Today, I'm going to speak on innovation, extending the life of special track work with laser welding repairs. First, I'd like to just kind of cover a little bit about a problem statement. It's a pretty well-known fact that a major cost to the railroads is the repair and replacement of manganese frogs and crossing diamonds. A study that was done about several years ago back by the FRA in 1997 tried to record some of the activities, and they indicated that $120 million is spent every year on replacing manganese frogs and crossing diamonds, and another $120 million on repairs. What was interesting from that study documented that the typical life of a new component was typically only about 57 MGT before it needed its first repair. And then each subsequent repair after that typically would get shorter and shorter. And the railroads continue to indicate that they may be lasting a little bit longer than this study indicated, but the problem is still the same, that repairs continue to degrade the frog until typically around the fourth or ninth repair, they're replacing the entire frog. So that is the problem. Holland then went into a process of developing a new technique we call laser welding. Officially, in the world today, this is typically referred to as laser additive manufacturing. It's a process that uses a laser beam to melt metal onto a surface. In this particular case, there are two different methods, but in our case, we're using what's called a hybrid method or a laser hot wire method, where an electrical current will preheat the wire that's going to melt to the surface, and then the laser beam melts the metal onto the surface. Again, this is a manganese material that we're placing on a manganese frog. This provides a very precise process with significantly lower heat in the process as well. This is all done robotically controlled, so that provides a very long reach for the repair. It's automated so that each layer is laid down through the robot without an operator working the operation, and that provides a much more precise layer pattern and interpass layer materials. However, in order to understand the process and materials that are used with laser welding, and how does this compare to existing processes today, the typical MIG welding process that's used today, either with a stick or a wire. So Holland utilized 5 different tests to evaluate the performance of this new technology and the materials, and compared that to base frog material, as well as the manual MIG welding process using 2 different off-the-shelf wires that are used today by most railroads. So I'm going to go through each of these quickly in order to share our results from testing. The first one is the Charpy impact test. This is a measure of the brittleness of the material, and certainly in this application, we do not want to have a very brittle material. On the far left are the results. It's done typically both with a cold and a hot temperature. So you see the blue dots are the cold results, and the red dots are the hot results of the test. The first bar is base frog material, and then the next 2 bars are the MIG welding process with 2 different brands of wire. In the middle there, the red bars indicate our initial testing that produced very poor results. So then we did further research and developed the technique so that, as you can see in the last 2 bars on the right, the results are very comparable now to the MIG welding process. And in fact, our preference for welding is the brand A formulation, because it does have higher impact resistance and is less brittle. The next test we utilized was a tensile test. Metallurgists often refer to metal toughness is the area under the stress strain curve from a tensile test. And it's one of the reasons why manganese is used for this application, is because of its toughness of the material. And so if we look at, again, comparing this to base frog material and other materials and processes, just to summarize quickly, the lower part of the lower graph, the coming off of the 60 KSI, is the base frog material. And as can be seen by this, the circles, the black circles, far exceeded that, and that's using the laser welding technique and the formulation that we are currently using. So significantly better in terms of the toughness of the material. The next was to look at how well does this material wear in this application as a train is passing over it. And for that, we utilized what's called a disc-on-disc wear test. We literally cut out discs of the material after welding, and then rotate the discs as they press against each other, apply a pressure. One disc is rotating, the other disc is resisting the rotation, and then you measure how much material wears off of the disc as based on the number of cycles. The results of that test are charted here. The lower the bar, the less wear occurs over the same number of cycles. The higher is more wear. Again, this is not an industry standard test in terms of a minimum requirement. And in fact, we were again looking for comparative results. And this clearly showed that the material formulation is really the key here. But again, the process using laser welding was being used today in MIG process as well. So again, the wear characteristic is very similar to the existing materials used today. The next and one of the most important characteristics is to look at the heat input while welding. And this is a test where we, again, utilized MIG welding and then did a cross-section of the materials. And the base material, when you do MIG welding, and if you exceed 500 degrees, which is kind of the benchmark that the railroads use for trying to repair a frog without exceeding that. However, that's very difficult to do with MIG welding because of the arcing process. And as can be seen in the top graphs and the cross-sectional views, there was significant grain growth of the base material underneath the weld. And in fact, there was also cracking in that area because the temperature did in fact exceed 500 degrees. And so this validates the target to stay under 500 in order to produce a longer lasting repair. The advantage, again, with laser welding is because it puts so much less heat into the melt of the base into the material. In that particular case, the lower graphs are shown of the laser process that there was significantly less grain growth and there was no cracking in the material below the weld. So excellent results under the heat input analysis. And porosity is another challenge when MIG welding, of course, because of the arcing process, there tends to be gas pores in the material. And as you can see in the center, the MIG welding, the gas pores are very visible in a cross section from the impact test. Whereas the laser process, the far left, there's no visible sign of porosity. You have to magnify it a bit in order to find any porosity at all. So the pores are not seen in the laser samples, even though there are very small pores there. They're very large and obvious in the MIG welding process. So again, a much better interpass layer characteristic. The next thing we did in order to validate the process is we did a side-by-side test at TTCI, the test facility. And in this case, we did one repair with MIG welding, and we did one repair with the laser welding. And I ran them. Unfortunately, the test did not last as long as we would like, not because of the material itself or the repair, but unfortunately, the wing rails broke twice. And so the test was stopped due to that problem. However, the laser weld unit did go past 67 MGT before the test was stopped and was continuing to perform and only needing slight maintenance grinding is part of the process. So results were good, but the test was stopped early due to problems with the wing rails. The very first field test was conducted. We actually did the repair in the factory and then installed the repair in Falls City Sub, which is north of Kansas City. That was installed 3 years ago. As of today, we are over 90 MGT on that frog, and it continues to perform extremely well. And after the first month of initial grinding, there's only been maintenance grind once a year on that frog, and it continues to perform and is in service yet today. Holland then developed a process to deploy this technology. It's very similar to a mobile welding technique. We have a truck that is designed to deploy a cart with a robot and the laser head on the robot. That is deployed either on track or can be deployed beside track if there's access and sufficient distance to reach. And the cart is deployed near the frog, and then the robot then repairs the frog directly behind the truck. Holland produces for every repair. We produce a production report. We take photographs before and after. We record the location, the milepost, and GPS coordinates, and the serial number of the frog or any identifying marks on the frog so that we can track its performance. And that is a daily report that would be emailed out after the repair is done. Holland also did a side-by-side test in the field with a railroad that repaired a frog on the same line. They were both done at the same time. One was using the standard MIG welding process. The other was the laser weld, and tried to create exactly the same repair. However, because the laser weld process is so much faster, we were able to repair an area that was 40% larger, and yet it was done in 45% less time than the traditional repair process. So it clearly demonstrated that the repair can be done faster, much larger and more complete repair can be done, which is also going to lead to longer life. So our field experience, we've had no major problems. We can deploy and pack up in 10 minutes. The estimated time is 3 times faster than MIG welding. And typical repairs can be done either a smaller repair in under 4 hours or 4 to 5 hours for a large repair. We went back and looked at all the repairs from last year, or looked at many of them. We completed 75 repairs. 6 of them are now over 100 MGT, 9 over 80, and 19 over 60. So they have been demonstrating, all of them, over a year of service now that we completed last year. The repairs can be done in very cold temperatures and on up to very hot temperatures outside. And the time to repair is dependent on the size of the repair. Recently, in the last month, we inspected 22 of those repairs. All have more than a year of traffic and service life now. Recorded MGT anywhere from 55 to 100. They almost all of them were in excellent condition. The only 2 that were in fair or good condition was because there are other underlying issues with the installation. So in summary, I can indicate that the laser welder has various benefits. First, obviously safety. Low fumes are given off. There's no flux is used, and so you don't have the fumes from the flux, and you actually use less material for the same repair. The operator isn't bending over, breathing in the fumes. The operator can also get up and move out of the way with a passing train on an adjacent track and not leaning over all day long with back strain. As I mentioned, the quality demonstrated through the testing as well as the field experience so far. Speed, I already mentioned as well. We can complete repairs in 2 to 3 times faster and can do a much better repair. That's going to obviously lead to significant cost savings, both in terms of repair cost and longer life of the repair for the frog repairs themselves, and not having to replace the frog completely in a much shorter period of time. So this brings me to the conclusion of my presentation. As can be seen here, this is the deployment process going on. Be happy to provide more information. If you do have any questions or would like to see more information, you can visit the Holland website, which is hollandco.com. Again, that's hollandco.com. And there'll be more information under a tab called Laser Welding under the welding section of the Holland website. And thank you very much for your attention and your interest in the laser welding process.